JavaScript runs on a single thread. One call stack, one thing at a time, ever. And yet, a Node server happily juggles 10,000 simultaneous connections, and your browser animates, fetches data, and responds to your clicks, all at once. That contradiction has a name, and it's the event loop. Today, we're going to watch it work, live, with real code. We're going to block it, we're going to race it, we're going to starve it on purpose. And by the end of this video, you'll be able to look at any async JavaScript and predict the exact order it runs in. But we have to start with the boring foundation everything else sits on, the call stack. So I'm writing the world's simplest breakfast program. First, a function called makeCoffee. It logs that it's brewing, and it returns the string coffee. Nothing fancy. And a second function, makeBreakfast. It logs that we're starting, it calls makeCoffee, and it prints whatever came back. Then at the bottom of the file, we call makeBreakfast and log that the script is finished. No promises, no timers, nothing asynchronous anywhere in sight. Let's run it. And the output is exactly what you'd expect. Start breakfast, brewing coffee, done coffee, script finished. Top to bottom, one line at a time. But the machinery JavaScript used to keep track of where it was, that's the call stack. And I want to draw it, because everything in this video depends on it. When the script calls makeBreakfast, JavaScript pushes a frame onto the stack. That frame is just a note saying, here's the function I'm running, and here's where I am inside it. Then makeBreakfast calls makeCoffee, so a second frame gets pushed on top. When makeCoffee returns, its frame pops off, and we're back in makeBreakfast, exactly where we left off. Push, pop, push, pop. Last in, first out. That's the whole data structure. But here's the rule that makes all of this matter. JavaScript has exactly one call stack, and it runs one frame at a time. While something is on that stack running, nothing else in your entire program can happen. Not a click handler, not a timer callback, not a network response. Nothing. Keep that in your head, because now I'm going to weaponize it. New file, blocking.js. And let me show you the dark side of a single thread. I log start, and then I set a timer. Set timeout. Fire this callback in 100 milliseconds. That's the contract we're asking for. And now, the crime. A while loop that does nothing but check the clock, over and over, for 3 full seconds. This is pure synchronous work sitting on the call stack. No pauses, no yielding, just a hot loop. So think about the race here. The timer wants to fire after 100 milliseconds. The loop occupies the thread for 3,000. Who wins? Let's run it. The start prints. Now we wait. And there it is. Look at the order. The loop finished after 3,000 milliseconds, and only then did our 100 millisecond timer fire. 3 seconds late. The timer wasn't broken. The countdown finished right on schedule. But the callback couldn't run, because the only call stack in existence was busy spinning in our loop. A timeout in JavaScript is not a guarantee. It's a polite request. So if the thread was busy, who was counting down those 100 milliseconds? Time to draw the full picture. On the left, our call stack. The one thread, running your JavaScript, one frame at a time. When you call something like setTimeout, or read a file, or make a network request, that work does not stay on the stack. It gets handed off to the runtime's native side. In Node, that's a C library called libov. In the browser, it's the web API is. This is where timers tick and sockets wait, completely outside your JavaScript thread. When the native side finishes, your callback doesn't jump onto the stack. It gets placed in a queue, a waiting room for callbacks that are ready to run. Our timer callback sat in this queue for almost 3 seconds. And the last piece is the star of the show, the event loop itself. And honestly, it's almost insultingly simple. It's a loop that asks one question, forever. Is the call stack empty? If yes, take the oldest callback from the queue and push it onto the stack. That's it. That's the entire magic trick. Now our blocking demo makes perfect sense. The countdown happened off the thread, in libov. The callback was queued after 100 milliseconds, right on time. But the loop couldn't hand it to the stack, because our while loop kept the stack occupied for 3 seconds. Async in JavaScript doesn't mean parallel. It means, I'll get to it when the stack is free. Okay, now that you have the model, let's stress test it with the classic ordering quiz. This exact question, in some form, gets asked in half the JavaScript interviews on Earth. New file, order.js. First, a plain synchronous log. Then a setTimeout with delay 0. Fire as soon as you possibly can. Next, setImmediate, which is Node's other run this soon function. Then a resolve promise with a dot, then callback. Then process.nextTick, which is Node specific and very special, as you're about to see. And finally, one more synchronous log at the end. 6 log statements, numbered 1 through 6 in source order. Here's my challenge to you. Pause the video right now and write down the order you think they print in. Seriously, commit to an answer. This is the best self-test for whether you actually understand the event loop or just nod along to diagrams. All right, let's see the truth. Run it. And here's the real order, straight from Node. 1, 6, 5, 4, 3, 2. Almost perfectly backwards, which I promise is a coincidence, but a fun one. Let's decode it. 1 and 6 first, because synchronous code always runs to completion before any callback of any kind. The stack must empty out first. That's rule number 1. Then 5, process.nextTick. This is Node's VIP queue. When the stack clears, before the event loop is allowed to move at all, Node drains the next tick queue completely. It jumps ahead of promises, ahead of timers, ahead of everything. That's why it's called nextTick. It runs before the loop takes its next step. Then 4, the promise callback. Promises live in the Microtask queue, which drains right after nextTick, and still before any timer or I/O callback gets a chance. And only then do the Macrotasks run, our setImmediate and setTimeout, the ones most people expect to see near the top. They come dead last. One more thing, and this is subtle. On this particular run, setImmediate beat setTimeout 0. You might see the opposite order on your machine, and both are correct. At the top level of a script, that pair is genuinely non-deterministic. Hold that thought, because in a few minutes I'll show you the one place where their order is guaranteed every single time. So we have 2 classes of queued work. Microtasks, like promises and nextTick, and macrotasks, like timers and I/O. The difference in how they drain is huge, and I want to prove it. New file. 2 timers, both at 0 milliseconds. And a promise chain. Then 3 microtasks, where each one only exists after the previous one finishes. If microtasks and macrotasks were fair with each other, you might expect them to interleave with the timers. Let's find out. Run it. Sync first, obviously. And then look. Micro 1, 2, 3, all of them, before a single timer fires. This is the drain completely rule, and it's the single most useful fact in this whole video. Between every callback, before the event loop moves on, it drains the entire microtask queue. Not one microtask. All of them. And if a microtask schedules another microtask, that new one runs too, before the loop advances. So the full priority ladder in Node looks like this. First, the nextTick queue, drain to empty. Then the promise microtask queue, drain to empty. And only then does the event loop advance to the macrotask phases, where timers, I/O callbacks, and setImmediate live. Every await in your code base, every .then, rides this ladder. And by the way, this is exactly what async await compiles down to. Every time you write await, everything after that line becomes a .then callback under the hood, which means it becomes a microtask. So when your async function resumes after an await, it resumes with priority, ahead of any timer, ahead of any I/O. Modern JavaScript didn't replace this machinery. It just gave it nicer syntax. But wait, if the microtask queue drains completely before the loop can move, what happens if it never empties? You can probably smell the danger already. Let's commit this crime too. New file, starvation.js. A function called greedy that counts up and schedules itself again with nextTick 5 million times. And the victim, a completely innocent setTimeout with delay 0 that just wants to report when it actually ran. We start the clock, we light the fuse with one nextTick, and every one of those 5 million callbacks will cut in line ahead of our timer. Let's run it. Node is now chewing through 5 million chain next ticks. And there. The chain finished all 5 million calls, and only then did our 0 millisecond timer fire, 334 milliseconds late. It never stood a chance. This is called starving the event loop, and the official Node documentation explicitly warns you about it. A recursive next tick, or an endless promise chain, blocks every timer, every incoming request, every piece of I/O in your process. It's the same disease as our blocking while loop, just wearing an asynchronous costume. Microtasks are a priority pass, and priority passes are easy to abuse. Now, I've been saying macrotask phases, plural, and it's time to make that precise. One lap of Node's event loop isn't a single queue. It visits a series of phases, in a fixed order, every lap. Let me draw the ones you actually need to know. First, the timer's phase. This is where expired setTimeout and setInterval callbacks run. Then the loop moves through some internal bookkeeping phases and lands in the poll phase. Poll is where Node actually waits for I/O, file reads finishing, sockets receiving data, incoming requests. If there's nothing urgent to do, the loop parks right here. After poll comes the check phase, which exists for exactly one API, setImmediate. And then the close phase, for cleanup callbacks like a socket's close event. Then the lap is over, and the loop starts again at timers. And remember the golden rule riding on top of all of this. Between every single callback, in any phase, Node drains the next tick queue, then the microtask queue, completely, before touching the next callback. The phases are the map. The microtask drain is the law. And this phase map finally lets me pay off the mystery from our quiz. setTimeout 0 versus setImmediate. New file, immediate.io.js. At the top level of the script, I schedule both. A timeout with 0 delay and an immediate. And then the same two calls again, but this time from inside an I/O callback. I'm using fs.read file to read this very file, and scheduling the pair from inside its completion callback. Same two functions, different neighborhood. Run it, and look at the top-level pair first. This time, setTimeout 1. But remember, in our quiz file a few minutes ago, setImmediate 1. Same machine, same Node version, opposite results. That's not a bug. At the top level, it depends on whether 1 millisecond has ticked over by the time the loop reaches the timer's phase. It's a genuine race. But the bottom pair, the one scheduled inside the I/O callback, that order is guaranteed. setImmediate always wins there, 100% of the time. And the phase map tells you exactly why. An I/O callback runs in the poll phase. The very next stop after poll is check, which is setImmediate's home. Timers don't get another turn until the loop wraps all the way around. Geography is destiny. Okay, we've spent this whole video breaking the event loop. Let's end by fixing it. Back to our original sin, the 3-second blocking loop. What if you legitimately have 3 seconds of CPU work to do? The classic answer is chunking. Do a small slice of work, then give the loop a chance to breathe. Let me build it. Same victim timer as before, 100 milliseconds. But instead of one solid 3-second loop, I write a function called chunk of work. It spins for just 10 milliseconds. Then it checks, is there still work left? If yes, it schedules itself again with setImmediate. And that little choice is everything. Because setImmediate is a macrotask, not a microtask. Between each chunk, the loop completes its lap. It visits the timer's phase, it visits the poll phase, it handles whatever is waiting. Our work happens in 10 millisecond installments instead of one 3-second hostage situation. Let's kick it off and run. And look at that. The timer fired on time. Same total 3 seconds of work. It finished after 3,000 milliseconds, just like before. But this time our 100 millisecond timer actually fired at around 100 milliseconds, right in the middle of the work, because the loop got its turns in between chunks. One warning before you chunk everything in sight. Notice I use setImmediate, not process.nextTick, and not a promise. If you chunk with microtasks, you're right back in the starvation demo, cutting in line forever. And for genuinely heavy computation, image processing, parsing huge files, crypto, the grown-up answer is worker threads, which give you a real second thread with its own event loop. Chunk the medium stuff, offload the heavy stuff. Let's zoom out and lock in the whole model. JavaScript is one thread with one call stack, and while the stack is busy, nothing else runs. Async AP is handwork to the runtime, and finished callbacks wait in queues. The queues are not equal. NextTick beats promises, and both drain completely before the loop advances a single step. The loop itself travels a fixed circuit of phases. Timers, then poll for I/O, then check for setImmediate. That map is why setImmediate always beats setTimeout inside an I/O callback, and why it's a coin flip at the top level. And the one commandment over all of it: never block the loop. Chunk your work, or move it to a worker thread. Everything you saw today was real output from real runs, and I genuinely encourage you to type these 5 little files yourself and race the queues on your own machine. If this finally made the event loop click, a like really does help the channel, and subscribe if you want more deep dives like this. Next up, we're building an entire HTTP server from a raw socket by hand. I'll see you there.